So, in our last class we started conductor and we have seen few properties of conductor. The most important one was the net field inside conductor 0. So, what we did in the last class, conductors are the material which freely allow charge to flow, right, and insulators are material, they are not allowing charge to flow, right. And this was the first property we discussed, that inside conductor under electrostatic condition net field has to be 0. So, under electrostatic condition net field has to be 0, right. So, when you subject a conductor to external electric field, there will be drifting of free electron inside, and that drifting takes place in such a way so that it try to cancel out the field produced by external agency. So, when conductor is placed in field, there will be movement of free electron till the redistribution of charges cancels the field produced by this external agency, right. So, what we have seen that this field will have effect in this direction, and as this field will have effect in this direction, these all electrons start drifting in backward direction. They try to get accumulated here, and here there will be excess of charge, and this side there will be deficiency of charge. So, this side will acquire negative charge and this side will acquire positive charge in such a way so that they together will produce field at this particular point exactly opposite to this field, so that field will become 0. This is for this particular point, same thing will happen for all the other points, right. So, this was the first point we discussed in the last class. So, external plus induced, this is the net field inside conductor, E net inside conductor, that we got 0, right. Then I took one more situation where a charge is brought. As we get this charge near to the conductor, this charge start attracting electrons. So, what happens here in this region, this density of free electron got increased, and this side there will be deficiency of charge. So, here in this region it will be a negatively charged region, and somewhere here it will be positively charged region, right. So, distribution will be something like this, and it will try to make whatever it is producing at this particular point. This is field produced by Q, and this induced one, this is induced charge. So, induced charge will produce field in this direction, E induced I am writing, I uninduced, so that the effect of this point charge at this particular point gets cancelled. So, same thing happens for every point on conductor. So, at this particular point this is producing field in this direction, and induced charge will produce field in this direction, and net field under electrostatic condition has to be 0. They will cancel each other. So, at each and every point on the conductor net field is 0. This is the first point, right. Second point, as field inside is 0, say we have given some charge to this conductor, right. Say we have given Q charge to the conductor. So, what we have just seen, this charge will get distributed in such a way this charge will get distributed in such a way so that the net field under electrostatic condition has to be 0, right. If there is net field inside, obviously charge will be still drifting. That is not the condition of electrostatic. Electrostatic means charge at rest. So, there will be movement of those free charge particles. So, when electrostatic condition is achieved, there will not be any movement at that moment. There is no net field inside the conductor. This was the first point. Now, we are talking about second point. So, if at each and every point on conductor field is 0, no matter whatever the situation, if field is 0, then if I take any part of the conductor, and I apply Gauss law, then as you can see that at each and every point field is 0, E at every point is 0, and according to the Gauss law, E dot ds is equal to q upon epsilon naught. If at every point on this Gaussian surface, imaginary surface, field is coming 0, that means the net charge enclosed has to be 0. So, this q has to be 0, right. That means whatever you are giving, that is completely appearing on the surface. No charge, no excess charge or extra charge can reside inside the conductor. This is second point, and that we have derived using first point. Field inside conductor is 0. If field inside the conductor at every point is 0, if you take the Gaussian surface, if field itself is 0, then there should not be any charge enclosed by this Gaussian surface. Here we are talking about net charge, right. So, first point, field inside conductor at every point is 0. Second point, there should not be any excess charge inside the conductor. Whatever you give, immediately that will appear on the surface of conductor. This is second point, right. So, excess charge always resides on the surface of conductor. This is second point. Now, let us see next one. As the field everywhere is 0 on the conductor, you have given some charge, and if everywhere field is 0 inside the conductor, everywhere field is 0, that means there should not be any potential difference between any 2 points on the conductor. Why? Because dV, potential difference, is E dot dr. Potential difference between 2 points is E dot dr with minus sign. If this E itself becomes 0, then this dV will become 0. dV will become 0, that means potential is constant. That means for this whole conductor, potential will have same value. So, whatever is the potential here, same is the potential here, same is the potential here, everywhere potential is same. So, this whole thing will behave as equipotential object. So, everywhere on the conductor potential is same. For example, if I say potential here is 2 volt, what will be the potential here? As field is 0, difference will be 0. As difference is 0, potential is constant, that means everywhere potential will be 2 volt, right. So, potential has to be constant, right. Let us see next point. So, potential is constant, electric field inside conductor 0, no excess charge can reside inside the conductor, whatever charge you are giving, that is appearing on the surface of conductor, right. Let us see another point. The electric field just outside the conductor. So, visualize that this is a charged conductor, and it has got charge something like this, right, and I take random direction of the field on the surface. So, if I assume that just outside the conductor, let field is in this direction, I do not know the direction, let it be making some angle with perpendicular. So, on this surface I will draw perpendicular, right. So, here on the surface I have drawn normal this way and say field is in this direction. If I assume that field is making angle theta, so you can see there will be two component of field. So, this electric field will have two component. One component will be perpendicular to the surface, that is E cos theta component along normal, and another component will be like this, E sin theta, right. So, we assume some generalized direction, and what I am saying is we resolve this field in two direction, one perpendicular to the surface, another along the surface. Look at the component along the surface. Because of this component you can see that charge here will experience force and it starts moving along tangential direction. As it starts moving along tangential direction, that means this is not the electrostatic condition. If any component of field is coming along the surface, the charges near to the surface here start experiencing force this way and they start moving. But in electrostatic condition there should not be any movement of charge particle. If there is no movement of charge particle, that means there should not be any component in this direction. So, for electrostatic condition, for this E sin theta has to be 0. If electrostatic condition is achieved, there should not be any component tangent to the surface of conductor, that means this component has to be 0. If this field is not having any component in this direction, that means this field is exactly along the normal to the conductor. It will have two components if it is like this, one in this direction, another in this direction. From simple reasoning we have concluded that the component of field along tangential direction has to be 0. If this component is 0, that means field must be in this direction. That means what we came to know, that under electrostatic condition the electric field must be perpendicular to the surface. There should not be any component of field coming in tangential direction, right. This point is clear. So, what we have concluded here, this has to be 0 for electrostatic condition. So, electric field just outside the charge conductor is perpendicular to the surface of conductor, right. Now, let us see one more thing. That means instead of field being this way, at every point field will be perpendicular to the surface. Here it will be like this, here it will be like this, here it will be like this, here this way, right. So, everywhere it will be perpendicular to the surface. Here instead of this way it has to be actually this way, right. So, you give charge to the conductor, or it is placed in external field, or it is placed in front of point charge. In all the cases the field just outside the conductor will be making 90 degree with the surface of conductor at that particular point, right. So, all these has to be 90 degree, right. So, all these angles wherever I take, So, this is another point, right. I hope it is clear. Let us see next one. So, we have talked about what would be the direction of field just outside. Let us find out what would be the magnitude of field just outside. So, I am interested in finding what would be the magnitude just outside, right, just outside. So, this is very small, just to make you understand I am drawing this big. So, I have taken a cylinder of very small size. So, some part of cylinder is inside the conductor and some part is outside. So, very small part is outside, right. Direction idea we already have from the previous discussion. Now, the magnitude we want to find out. So, just now we have figured out that right. So, at this particular point or for this area you can see that field is in this direction, right, and inside it is 0. This is very small part, right. So, if I apply Gauss law to find out the magnitude of field just outside, then what I can do, I can calculate the flux associated. Let this area be A. So, as field is perpendicular to surface and size of this one is very small, everywhere on the area field will be like this. So, I can directly write flux. So, this side I need to write flux, this is nothing but flux enclosed by closed surface, right, and according to Gauss law this is Q upon epsilon naught. So, the flux associated here I can see that E times A will be the flux associated plus here you can see that field is 0 inside the conductor. First point was field inside the conductor is 0. So, I am using first point here, as field itself is 0, flux associated will be 0. That will be equal to what would be the charge enclosed? Let the local surface charge density is sigma. Let the local surface charge density there is sigma. This is very small cylinder just passing through conductor, some part is outside and some part is inside, right. So, this is the Gaussian surface, this is our Gaussian surface, and through this Gaussian surface we are calculating flux. For this surface, so I got flux Ea, this surface I am getting flux 0, and as you can see that for this curved surface the line will be parallel like this. So, there will not be any line cutting this area, right. So, there will not be any flux associated with this surface. So, first surface, second surface, third surface. So, first surface we wrote it here, second surface field itself is 0, and third surface no flux is associated, I am not writing anything over there. Now, how much is the charge enclosed? If the area of this one is A, area of this one is also A, if you multiply surface charge density to area, you will get the charge. So, charge enclosed by this Gaussian surface is whatever coming inside, and that is sigma into A divided by epsilon naught, right. So, the field inside we are getting, field just outside we are getting A gets cancelled out, sigma upon epsilon naught. So, the just outside the conductor, the direction of field will be perpendicular, and the magnitude of field is given by sigma upon epsilon naught, where sigma is the local surface charge density. Everywhere the surface charge density will be different. Everywhere surface charge density will be different depending on how sharp the edge is, right. Flatter it would be, the density will be lesser. Sharper it would be, the density will be more. Now, let us see this next point. So, if I just take a part somewhere here and part somewhere here, right, through this whole conductor, if I just take the part, right. So, some small part I have taken here and some small part I will take here. So, it will be something like this, very small part, but I am drawing little big diagram so that you can understand. So, very small part I have taken from here and very small part I am taking here, and they must have the same potential. So, if I assume that surface charge density here is sigma 1 and surface charge density here is sigma 2, and the radius here is r1 and radius here is r2, and they have the same potential, right. The condition is the potential is same. So, potential here and potential here must be same. If charge is distributed on the surface, right, what is the potential of that? So, if I say I have one sphere and charge q is distributed over the surface and the radius is r, the potential formula is kq divided by r, right. So, this is the formula for potential. So, I can write the potential here and that must be the potential here. I will equate and let us see what we are getting. So, I am equating potential for very small part somewhere here, very small part somewhere here, visualize it this way, and take very small part somewhere here, here, because of this part the radius of curvature here is say r1 and here the radius of the surface is say r2, right. What I am doing, as we already proved that inside everywhere field is 0, the potential here and potential here must match, right. So, the local surface charge density here I am considering say sigma 1 and local surface charge density here I am considering sigma 2. So, this I am drawing here and this I am drawing here. I hope the diagram is clear, right. As the part is very small, I can assume that almost uniformly charge is distributed, right. Similarly, here almost uniformly charge is distributed as part is very small. So, I have taken very small part here and very small part here, so that I can write a single radius of the surface, right. So, here potential and here potential must match. Let us call it V1 and V1, V1 and V2. So, potential here is KQ, KQ, Q is sigma 1 into surface area, surface charge density into surface area, 4 pi r1 square divided by r1. Same thing I write for 2, same thing I can write for 1, I have written this for 1 and now I will write for 2. So, this can be written k sigma 2 into 4 pi r2 square divided by r2. If I simplify, see what we are getting. So, this and this will get cancelled out and we are getting here sigma 1 r1 is equal to sigma 2 r2. That means I am getting surface charge density inversely proportional to the radius of surface. So, the 2 points we have seen, first point was that the electric field here depends on the local surface charge density sigma upon epsilon naught. Second thing we are seeing that depending on the curvature, you are going to get surface charge density. If radius of curvature is infinity, for flat surface radius of curvature is infinity, then the surface charge density will be 0. If radius of curvature is 0, consider a very small surface where radius is almost tending to 0, very sharp surface, then you can see that if I substitute radius there 0, then I will be getting sigma infinity, right. What does that mean? Let us see that. So, this is what we have concluded and this is what we have derived, right. Now, what I am saying is, let us first erase this part, then it will be more clear. assume that I have taken object something like this. You can see here sharpness is more as compared to sharpness here, it is almost flat, and here it is sharper, right. So, if I give q charge to this one, the way q charge distributed is given by this expression. Here if you try to draw circle, the radius will be very small, and here if you try to draw circle, the radius will be very large. If I want to draw circle somewhere here taking a small part, then the radius will be large, right, very large. Similarly, I can draw circle taking this part, it will be something like this, right. In 2 dimension I am talking about, that is why I am taking circle here, right. Now, so depending on the radius what we are getting, we will get the surface charge density, and it is inversely proportional to the radius what we are getting. That means if I give q charge to this one, here because the radius is very small, the surface charge density will be large, right. As you start going this way, the surface charge density will be small. Then again here you can see so distribution will be something like this. Here it will be, density will be more as compared to the density here. How we are concluding this? Sigma is inversely proportional to 1 upon r, right. R is, if I take a small part over here, the radius of this part. So, field outside, just outside will be perpendicular to the surface, and the magnitude of field is given by sigma upon epsilon naught, right, just outside. If you go to some distance, you cannot apply this formula, because this formula is meant only for just outside, right. And equating potential for this small part and this small part, or any two combination, we were getting sigma inversely proportional to r. So, accordingly there will be charge distribution this way. So, I hope this point is clear. The surface charge distribution may be different at different points, you can see. So, depending on the shape we have, if I take conducting sphere and I give charge q, take conducting sphere and I give charge q, every part the radius of curvature will be same, charge will be uniformly distributed, right. But if I have any other shape conductor, like any potato shape conductor or any journal shape conductor, then for different part the radius will be different and you are going to get density different. So, density might be different depending on the shape of the conductor. So, this point is also clear. So, inside, outside, over, right. Now, let us deal other situations using the concept what we have just seen. Field inside conductor is 0, first point. There is no excess charge residing in the conductor, right. Just outside, field will be perpendicular to the surface, and the magnitude of field was sigma upon epsilon naught, and how the charges will be distributed, that is inversely proportional to the radius of curvature of conductor at that particular point, right. So, using these points we will see other situation. So, conductor with cavity. So, from conductor if you scoop out some part, from conductor if you scoop out some part, the same number of proton and neutron you have eliminated, right, from the conductor. So, it will be initially electrically neutral, right. If I give some charge to this one, assume that I am giving some charge q to this one. So, what will happen, that here everywhere radius is same, this charge is uniformly distributed. So, any charge given will get uniformly distributed and the effect of these charges at any point inside the conductor, we have seen that E is equal to 0, right. There is no other field and external charge in the space. So, it is the responsibility of charge appearing on the surface alone to make the field at every point inside the conductor is 0. So, whether there is some material or not, it is not going to make any difference. So, when cavity was not created, everywhere here field was 0. When cavity was not created, throughout the whole conductor, everywhere field was 0. Now, if I scoop out some part, I have removed same number of proton and electron, the condition is still valid. So, because of this outside charge, everywhere on conductor and inside cavity, field is 0, you can see. And same thing we have derived for in electrostatic 3, we have derived the same thing, that because of the charge spherical shell, everywhere field will be 0, right. We have derived it there. So, same situation, field was 0, right. So, it is the responsibility of the charge appearing on the surface to make electric field 0, and we have seen that whatever charge you are giving, that whole charge will appear on the surface. Extra charge or excess charge cannot reside inside the conductor, right. Okay. So, this is about what will happen if I give charge to the conductor, whole charge will appear on the surface, and because of that charge inside cavity and on the conductor, field will be 0. Now, let us keep the charge inside the cavity. If I place the charge here, initially let us keep it at the center, so that we can easily analyze. So, I am keeping a charge at the center here. So, if I keep the charge at the center, you can see what will happen. So, I keep say plus q charge, man I do not know how the distribution is. So, let us remove it for time being. Okay. We have placed a charge inside the cavity exactly at the center, right. Now, according to Gauss law, E dot ds for this surface must be equal to charge inside upon epsilon naught, right. But the problem here is on the conductor field has to be 0 everywhere. So, here everywhere field has to be 0, our first point. So, as here field is 0, this side term is coming 0. But you can see there is plus q charge here, right. This side term won't be 0 if the charge inside this Gaussian surface is only this one. So, if this side it is 0, it has to be 0 on other side. It can be 0, we are sure about this charge, that is plus q, and if there is some negative charge appear on the inner wall of cavity, let us say minus q dash, then this plus and this minus can make it 0. So, if distribution is something like this, then you may get 0, and for this term to become 0, this must be same as the magnitude of this one. That means q dash will have the same magnitude as that of q. Only thing is charge opposite to make the electric field everywhere 0. So, what will happen that as you place the charge inside the cavity, this charge start attracting the electron and they start drifting, because this try to create the field here. This is trying to create the field here. As field comes into picture, immediately there is a drifting of electrons opposite to the field. So what will happen, those extra electron, sorry, what will happen, those electrons start drifting towards the wall of cavity, and they keep drifting till they produce the field here in opposite direction. Because once the net field here becomes 0, once net field here becomes 0, then there is no further movement. Once the net field here becomes 0, there won't be any further movement, and this whole thing will come into electrostatic condition. So charge start drifting towards the wall of cavity, and on the inner wall of cavity equal amount of the charge will appear, sign opposite, right. So first point we got, whatever you are keeping here, same charge is appearing on the wall of cavity to make the net field inside the conductor 0, right. So let us draw neat diagram. So till now we place plus q at the center of this spherical shell, and we got minus q on the inner wall of the cavity, right, and its charge center must be such that they will cancel the effect of each other at this particular point, right. But the problem is we did not give any charge to the conductor, we did not give any charge to the conductor, right. Inner wall got minus q charge. For conductor to remain electrically neutral, the plus q will appear on the outer surface, but conductor was not having any charge. We are not touching our charge to the conductor, we just place the charge inside the cavity. So charge is not touching the conductor, right. So the net charge on the conductor must remain 0. So inner wall, if it is getting minus q charge, outer wall must get plus q charge, because charge cannot be inside the conductor. So obviously the remaining charge will appear on the surface of the conductor. So plus q charge will appear like this on the surface. And the field pattern will be something like this. So from this plus q charge, lines will start and terminate on the walls of the cavity, right, and here again from these plus q charge, line will start originating and going till infinity. So these lines, outer lines, are due to the charge appearing on the surface, and here whatever positive we have, same negative we have, so all the line originating from the positive charge will terminate at these negative charge. So this will be the field pattern in space. Now the question is, instead of keeping it here at the center, if I keep somewhere else, somewhere here, right. So let us see. So I now want to place charge somewhere here. Again using Gauss law and drawing Gaussian surface passing through conductor, I can say charge enclosed by Gaussian surface has to be 0. So one thing is sure, that charge appearing on the inner wall of the cavity has to be minus q. Now you are not placing charge at the center, right? You are not placing charge at the center. So its charge center must be such that it will cancel the field produced by this. So obviously if this charge gets uniformly distributed, then it cannot create the field exactly equal and opposite. So obviously now the charge center of this one must lie over here. Charge center of this one must lie over here, then only this will create the field opposite to the field created by this one in this direction. So this one is creating field in this direction, this charge center if it is lying here, minus q, visualize here minus q charge, and that will create the field in opposite direction, then only they can get cancelled out. So obviously the distribution here has to be non-uniform, right. So when you are not placing charge at the center, the inner wall of cavity will have non-uniform distribution. What about charge appearing on the outer surface, because this conductor has to be electrically neutral. So minus q appears inside and plus q will appear. Now plus q will take the responsibility to make the electric field, because of plus q, everywhere 0. So if our outer surface charge is non-uniformly distributed, then it cannot make the electric field inside 0. So what will happen, this charge will get uniformly distributed, then only it can make the field inside 0. Again electrostatic third, we discuss that when charge is uniformly distributed, then only you get electric field everywhere 0 inside. And there I told you, if this charge is non-uniformly distributed, for example here say density is more as compared to the density this side. So this is producing more field this way and this is producing less field this way, net field will come in this direction. So field can be 0 inside the spherical surface only if the outer surface charge is 0. So this alone, listen carefully, this alone makes field everywhere 0, and these two in combination making field everywhere on the conductor as well as outside 0. Important point, because this we will extend for any shape conductor, right. Again the charge appearing on the outer surface will have electric field every point inside 0. So because of this charge everywhere, whether on conductor or inside cavity, field is 0. First point. Second point is these two in combination, charge inside the cavity and charge appearing on the inner wall of cavity, they in combination will make electric field any point on conductor as well as outside 0. So if I ask what is the field created by these two at this particular point, 0. If I ask field created by these two at this particular point, 0. If I ask field created by this one at this particular point, 0. Field created by this one at this particular point, 0, right. And this is valid for any shape conductor that we will see later. So now let us see how field lines will be there in a space. See, so lines will be originating from positive charge and terminating at negative charge appearing on inner wall of cavity. So lines are starting from here and get terminated at the negative charge appearing on the wall of cavity. Outside charge, as it is uniform, the field lines will be radially outward in every direction, right. And I already told you that lines will make 90° at the surface. So, here it will be 90°, here it will be 90°, here it will be 90°. So, field lines just outside the surface will be perpendicular to the surface. Here also they all are perpendicular, right. Now, I hope it is completely clear what will happen when we move this charge. So, when we move this charge, this distribution will get affected, but there is no effect of this movement on the charge appearing on the outer surface of the conductor. That will be uniformly distributed. Inside one will become non-uniformly distributed when you move it from center of the conductor, center of the spherical shell to any other location, right. So, as you start moving, this distribution will become non-uniform, right. Let us see another point. So, just now I have discussed what happens, we have a spherical shell, conducting spherical shell. Now, let us take a generalized shape, any shape conductor, and we have a charge inside cavity. So, charge inside cavity and we are not giving any charge to this conductor, right. So, conductor is not given any charge. This is a simple situation. First understand the concept here, then we make the situation little complicated. So, when you place the charge here, again when I draw Gaussian surface this way, the same logic I can extend here. By electric field everywhere is 0, electric field everywhere is 0, E dot ds close is in divided by epsilon naught, and as electric field is 0 everywhere, the net charge coming inside has to be 0. So, q in is 0, that means this charge and charge appearing on the surface of cavity, they must cancel each other to get this value 0. To get this value 0, the charge on the surface of cavity must be minus q, same logic we have just seen, right. So, charge appearing here will be something like this, minus minus this way, right. This is first point. Second point, as conductor was not given any charge and it was not earlier having any charge, so it has to be electrically neutral even after redistribution. Same amount of positive charge will appear on the outer surface of conductor. So, I will place some charge on the outer surface. I already told you that distribution will be non-uniform, right, depending on the radius. Something like this, right. So, as you understood this point, I will erase this one. And this is also clear. So, this is plus q and this one is minus q. Again the same logic, these two listen carefully, the charge here and the charge appearing on inner wall of cavity, they will cancel the effect at any point on the conductor. So, this plus q will produce charge, produce field in this direction, E because of plus q, and because of this minus q, E will be like this and they will cancel each other. Even if I go outside, somewhere here I go, this positive charge will produce field in this direction and this negative charge will produce field in this direction and they will cancel each other, right. So, they will have in combination net field on the conductor and outside conductor 0. This is first point. Second point, I already told you whatever charge appearing on the surface is the responsibility of that charge to make electric field inside the conductor or on the conductor and inside the cavity everywhere 0. So, this plus q completely will produce field at any point on the conductor 0 and as well as inside the cavity 0, right. Let me write these 2 points so that it is more clear. So, what I am saying is electric field produced by Q and electric field produced by minus Q, that is right, charge on inner surface of cavity. This combination will have value 0 where value 0 where at any point on conductor as well as outside conductor. Right, this is first point. Second point was charge appearing on the surface of conductor. In this situation, electric field due to charge on outer surface of conductor electric field due to charge on outer surface of conductor is 0 where on conductor as well as any point inside the cavity on conductor as well as any point inside cavity. Now you can clearly see what I have written. So, two conclusions we have drawn. Irrespective of the shape of the conductor, if charge is just kept inside the cavity of conductor, then this charge and this charge, they in combination will make field here 0 and here 0, right. And the second point we have seen that whatever appearing on the surface of conductor, because of that field here and field here both will be 0, right. So, I hope these points are clear. Let us move to next one. Let us see one animation so that you will be having idea what is happening, right. So, I already told you ki if you displace the charge inside a spherical cavity, then on the wall of cavity charge distribution become non-uniform. So, here this is one simple animation, by that you will be having idea what is happening inside. So, this charge if I just move inside, what will happen that as I move this charge inside, you can see the distribution. So, as this charge goes here, distribution here get increase, as this charge comes here, distribution here get increase. Let us see once again. So, as it goes here, their distribution will get increase, right, charge density will get increase. As it comes this side, here it is getting increase, and you can see during the movement there is no effect on the distribution on the outer surface, because its own responsibility is making field here and here 0, which is already is 0, right. So, this will not change when you are changing this one, only this will change to make electric field at this particular point. This and this, whatever are appearing on the surface of cavity and the what is inside the cavity, they together has to make field 0 here. So, as you are moving this charge particle, the field here will get altered. To cancel this field, this distribution must get changed. So, inside distribution will get affected because of the movement of this charge inside the cavity, but the outside will remain unaffected, right. Let us see one more animation. So, I am keeping this charge as it is and I will bring another charge, right. So, distribution of charge here, because this is a positive charge, here this will be a negative distribution, right. So, minus will be here in this region and somewhere in this region it will be plus, right. So, in this region this will be minus, something like this, right. Now, keeping this one fixed, if I start moving this one, so what will happen that as you are keeping this one fixed, this is not going to get affected, this will remain same, because this and this together they are cancelling each other here as well as here, But now the problem is the Q coming on the surface alone cannot make field here 0, because this is also creating field, So, this is creating field here in this direction. So, this has to create field in opposite direction, then only they will get cancel out. So, in combination, now I am adding one more line in the previous discussion, listen carefully. The charge appearing on the surface of conductor and charge outside the conductor, they together will make the field inside conductor as well as inside cavity of conductor 0. So, their combined effect, this charge and the charge appearing on the surface, they will cancel each other on the conductor as well as on the cavity, right. Earlier we did not have this charge. So, when we did not have this charge, I said this alone will make the field everywhere 0. Now, when this charge will come into picture, this will also create field and it is responsibility for this charge to cancel that field, so that net field on conductor you will get 0, right. So, what if I start moving this one? Let us see. So, when I start moving this one, you can see that here the negative charge density gets increased, and as I move it out, then this will get decrease. Let us see once again. So, as you are moving this charge, here density is getting increased, similarly here density will get affected, but there is no effect on surface charge density on the wall of cavity, right. So, distribution on the wall of cavity can only get altered when inside charge will get displaced. So, this distribution will get only affected when this charge will get displaced, and the outside one will get affected when I bring another charge outside the conductor, or instead of putting charge I can put electric field here, right. So, if instead of charge I have electric field, then this outside surface charge and the field what you have applied, they will cancel each other at this point as well as this point. So, this distribution is affected by external agents. It might be a point charge, it might be external field, right. So, I hope now it is clear. You can see animation once again. Right. Now, let us see next one. Okay, let us do one thing before getting into next one. Let us move everything, this one, so that you will understand how the distribution is getting affected. See, so first I am just moving this. So, on the surface distribution is getting affected, then I am moving this, then on the surface of cavity distribution is getting affected. So, one by one I am doing this, right. And these lines are always perpendicular to the surface, right. These all lines are always perpendicular to the surface. These lines are always perpendicular to the surface. Okay. And there will be lines here also. I did not want to make the diagram complicated. I am just showing you few lines and the distribution. So, our focus is mainly on the distribution, right, how distribution is getting affected due to movement of charges, right. So, now I hope whole concept is completely clear. We talk about basic point associated with the conductor, and using those basic point we are understanding or analyzing the different situation. So, I started with the spherical shape because it is easy to understand, then I took a journal shape, right, and we are seeing that same concept when we apply here what type of distribution we will get. So, let us move to next one. So, let us see one example before getting into other points. So, simple example, a point charge is placed in front of a conducting sphere as shown in the figure. Find the potential and field due to induced charge at point P. So, what will happen that in front of conductor when you are placing charge, obviously here it will attract electron, here there will be negative charge. It will be something like this, right. So, I am drawing approximate diagram. The distribution will be something like this. No charge was given to this one. So, whatever appearing, that is induced charge, right. So, you brought this charge near to conductor, this charge will attract electron, this side it will be excess and this side it will be deficiency. That is why I am drawing positive here and negative here, right. And the point what we have learned, that this distribution will take place in such a way so that it will cancel the field produced by this one at every point. So, if I talk about field first, okay, field first. So, field I can directly write whatever field this is producing at this particular point in this direction, same field is produced by induced charge in opposite direction, because net has to be 0, net on conductor has to be 0, and field produced by capital Q and field produced by induced charge this combination has to be 0, and you know the field produced, that means direction has to be opposite, right. So, I am just writing magnitude. I can say the magnitude of the field produced by Q must be equal to field produced by induced charge. And this you know from charge at distance r, what is the field? 1 upon 4 pi epsilon naught k q divided by r square is the magnitude of field produced by induced charge. This is our first part. Okay, how much is the field produced by the induced charge? This one. Now second part is, what is the potential? Find the potential due to induced charge, not the net potential, find potential due to induced charge. Okay. So I will erase all this. So first part is clear. Now we are solving second part. Let us talk about the potential. What we know, that everywhere potential will be same because electric field inside is 0. So you take any point, potential at this point will be equal to this point will be equal to this point, any point potential is same, right, every point potential is same. That means whatever the potential here, same is the potential here. First thing I can write, potential at C will be equal to potential at P. C is the center of a sphere, potential at C will be equal to potential at P, right. Potential at C. So induced charge will produce potential here and this charge will produce potential here. Potential is scalar quantity, I can directly add, right. So potential at C, potential due to charge Q plus potential due to induced charge will be equal to potential at P. So potential, this I am writing at C. So this is at C, and similarly same thing I write potential by Q and potential by induced charge where at P. Now this conductor was electrically neutral, and when you are bringing a charge, point charge, and placing it here, this will remain electrically neutral. That means whatever positive we have, same as the negative. Whatever positive we have, if same as the negative, and all the charge elements are at the same distance. So I can write dq k divided by r as the potential contribution by a small element. So potential contribution by the small element on the surface is k dq by r. Potential scalar quantity I can add. As you can see, this will contribute to negative potential and these will contribute to positive potential. These will contribute to negative potential, these will contribute to positive potential, or I can directly say this negative charge will be equal to this positive charge because it was earlier electrically neutral. So when you add this one dq, as it is a scalar quantity, so positive negative will cancel each other and you will get 0 over here, right. So this is potential at C by induced charge. I can substitute this value over here at C, induced charge contribution 0, at C contribution of this Q charge is at distance d. I can directly write here K Q by d plus this I got 0, and now I need to write this at P. Q charge contribution here at P, that is kq by r, kq divided by r plus induced charge potential at P, that is the question. So I need to find out this value. So I will get this term on other side. So potential due to induced charge is kq divided by d minus kq divided by r. We got field, we got potential. Using points we have discussed earlier, right. Potential everywhere is same and inside the conductor field is 0. Okay. Let us see next one. Charge distribution on large conducting plate. So, very thin plate, this is very thin plate and I am giving plus q charge to it, right. So, when I give plus q charge, some amount of charge will appear on this surface and remaining amount will appear on other surface. I do not know how charges are getting distributed, right. So, out of capital Q, say x comes this side and q minus x comes this side and we want to find out how the distribution is. So, only one unknown, that is x. Now, because of this charge appearing on this side and because of this charge, the net effect at any point inside the plate has to be 0. And if you remember, because of infinite sheet, the field we got at this particular point was sigma upon 2 epsilon naught, sigma upon 2 epsilon naught. Electric field will derive this result that I am going to use. This is the field created by one side charge only, right. That means, if this side charge is x, is surface charge density sigma is surface charge density sigma is x divided by a, where a is the surface area, a is surface area. So, one side charge is say x, the formula is sigma upon 2 epsilon naught, x divided by total area, plate is very large, right. So, whatever be the total area that we divide, then we will get sigma, right. So, field expression what we are getting because of this one side x charge, that is 2a epsilon naught, right. So, do remember this result, whatever charge is appearing on one surface, because of that field is given by charge divided by 2 epsilon naught, right. From here onwards I am directly using this result. So, instead of using sigma upon 2 epsilon naught, I will directly use this result, it is convenient to write. So, because of this x, the field coming at this particular point will be away from the distribution in this direction and that will be x upon 2 epsilon naught. As on other side of the plate, charge is q minus x, that is producing field charge divided by 2 epsilon naught, right. And the condition that field at point P has to be 0. So, field at point P has to be 0, that means for field to be 0, this magnitude must be equal to this magnitude. I can equate x divided by 2a epsilon naught to q minus x divided by 2a epsilon naught. So, these two will get cancelled out and you can see that we are getting x is equal to q by 2. That means, when you give q charge to the conducting plate, half of the charge will come this side and another half will come on other side. So, this side it will be q by 2 and this side it will be q by 2 and distribution will be something like this, right. So, plate will have two surfaces, one this side surface, another this side surface. Whatever charge coming on this side surface, that will produce field in this direction as well as this direction. Similarly, what I am facing, if I put a plate in front of me, then what I am facing, that surface, whatever charge it is containing, that will produce field towards me and on other side it will be away from me, right. So, this charge producing field at this particular point away from distribution. This charge producing field at this particular point away from distribution. So, these two charges are only producing field. To have net field 0 here, they must balance each other, that is what we have done. Net field has to be 0. So, when to have net field 0, the charge on both sides of the surface must be equal. So, when you are giving a Q charge, then it will get equally divided, right. So, I hope whatever we have discussed today, all the points are clear, and in the next class we will be using those points for other situations also. So, today I discussed the few situations, and next class we will be taking up other situations, right. So, that whole concept of conductor will get clear. It is very important topic, question frequently asked from this topic, right.